Hello everyone. Let's take a closer look at static equilibrium problems and how they relate to other topics that we have discussed this year, such as balanced forces and balanced torques. Let's take a look at what it means for objects to be in static equilibrium. The word static here means that objects are not moving. Typically, when we describe objects in equilibrium, we refer to balanced forces and torques on the object, which would imply a constant velocity of 0 or some value. When we talk about objects being in static equilibrium, we refer to objects that have balanced forces and torques that have 0 velocity. They're not moving at all. We see objects in static equilibrium all around us, such as signs hanging from buildings, objects leaning against walls, brakes being applied to wheels like on the bicycle, and a mousetrap ready to be sprung. All of these objects have forces that are being applied at various points to prevent the object from either translating or rotating. The main concept we want to apply in static equilibrium problems is that the sum of the forces and the sum of the torques equals 0. They must equal 0 if the object is not going to translate or rotate. Here we see the vector equations for the sum of the forces and the sum of the torques equaling 0. These are vector equations. However, practically, to solve static equilibrium problems, we must look at magnitude equations. Typically, we set the sum of the forces in the x and y directions equal to 0, as shown here, and the sum of the counterclockwise torques minus the sum of the clockwise torques equal to 0, also shown here. When these equations are satisfied, then the object can neither translate or rotate, and it will be in static equilibrium. Let's take a look at a few specific problems. Here you see a problem where a wooden board is leaning against a frictionless roller at the top of a wall that is 3 meters high. The board is 6 meters long and has a mass of 45 kilograms. The board remains in equilibrium if the angle theta is greater than or equal to 70 degrees, and slips if theta is less than 70 degrees, as shown in the picture. You are to determine the coefficient of friction between the board and the floor. Pause the vodcast here and try drawing the free body diagram and writing the force and torque expressions for this problem. Okay, let's see how you did. Here you can see the 4 forces acting on the board. Did you get the normal force from the roller and the force of friction working in the right direction? Now let's see what the force and torque expressions look like. Here you see the expression for the sum of the forces in the x direction, the sum of the forces in the y direction, and now the sum of the torques. We use the roller at the top of the wall as the axis of rotation because that is the point around which the board will rotate without translating. Let's take a look at solving the problem now. We are trying to find mu sub s, the coefficient of static friction, at an angle of 70 degrees, which is the limit for not slipping for this problem. We know that mu sub s is equal to the force of friction divided by the normal force, or F sub f divided by F sub n. So we need to find expressions for the force of friction and the normal force with the given information. From the vertical force equation, number 2, we see that the force from the roller is equal to that quantity Fg minus Fn over cosine theta. Substituting this expression for Fr into the horizontal force equation, number 1, we obtain the force of friction is equal to that quantity Fg minus Fn times sine theta over cosine theta, which is also equal to then that quantity Fg minus Fn times tan theta. This is then substituted into the torque equation, number 3, to get the expression Fn is equal to the force of gravity times that quantity d minus L over 2 cosine theta plus h tan theta, all that divided by d plus h tan theta. Now, since d is equal to h over tan theta, And we've got the trig identity, 1 plus tan squared theta is equal to 1 over cosine squared theta. We can simplify this expression to the normal force is equal to Fg times the quantity of 1 minus L cosine squared theta sine theta divided by 2h, which we will then call equation number 4. Now that we have the expression for the normal force, we need an expression for the force of friction. We saw a moment ago that the force of friction is equal to that quantity Fg minus Fn tan theta. If we substitute the Fn equation, number 4, that we just found, into this expression, we will get an expression for the force of friction, which will be equal to Fg L sine squared theta cosine theta divided by 2h, which we will call equation number 5. Now we can find mu sub s. That's going to be that force of friction divided by the normal force. Those two equations we just found, equations number 5 and number 4. We get the final expression then for mu sub s is going to be L sine squared theta cosine theta divided by that whole quantity 2h minus L sine theta cosine squared theta. Plugging in all our known information from the problem, then we'll get a value of 0.34 for the coefficient of static friction. Now I suggest trying this problem on your own, then checking your work with the work that I've shown here. Here we have an arrangement of fixed pulleys attached to a 70 Newton block of wood. We want to know the tension in the upper string attached to the ceiling at the top when this whole system is in static equilibrium, as seen in the picture. Drawing the forces in the picture allows us to see the tensions in each string more clearly. Tension A is equal to the applied force F, because the tension in the string must equal that applied force F if there is no motion. Tension B is equal to 2 times tension A, because there are 2 tension A's in the downward direction and 1 tension B in the upward direction, acting on that pulley B. The tension C is equal to 2 times tension B then, or 4 times tension A. Finally, tension D in the string that is attached to the ceiling is 2 times tension C, or 8 times tension A, which is also 8 times that force F. We also know that tension A plus tension B plus tension C has to be equal to the weight of the block, Fg, because they're all attached to the block. In other words, 7 times F is equal to Fg, or F is equal to Fg divided by 7. That's going to be 70 newtons divided by 7, or 10 newtons. Now, if the force F is equal to tension A, and tension A is equal to 10 newtons, then tension D, which is 8 times F, is going to be 8 times 10 newtons, or 80 newtons. Well, I hope this vodcast was helpful in reviewing some of the main concepts of static equilibrium problems. You may view this vodcast as many times as you like, and as always, feel free to ask questions in class, and good luck on the test.